All right. So a very important result, delta method. So in this lecture, we will continue with our discussion about deriving different sorts of limiting distributions or asymptotic distributions. Okay, so maybe we can just read this part together. So essentially, we will use this application called functions of sample moments, that is your statistics, is composed of different sample moments, like the average or the average of the squares or average of the cubics. And that's how you construct a statistic, right? Especially our Pearson correlation is an example of that. And we will show you how we can derive the asymptotic distribution of your sample Pearson correlation. So let's just read this part together. We continue investigating the implications of the Slutsky theorems. Here we study the Kramer's theorem. Actually, this is what we also call as delta method. Yeah. On the asymptotic normality of functions of the sample moments through a Taylor series expansion to one term. Yeah, Taylor expansion is commonly used in deriving asymptotics, essentially. The analysis of the asymptotic distribution of the t-statistic, right? T-statistic we all learned about, given the previous lecture, may be extended to d dimensions as follows. Okay, so this is central limit theorem. This is the covariance matrix. And from the law of large numbers and with some of the help of Slutsky theorem, we can actually have the sample covariance matrix 1 over n times this, because we're talking about a vector sense. So xi minus xn bar is a vector. Xi times x minus xn bar transpose is another vector. So their product is actually a matrix. But we're doing the outer product, not the inner product. Okay. And this converges to this covariance matrix. But this, I can say that this only applies to the low dimensional scenario where dimension is less than n. If the covariance matrix is non-singular, positive definite, then we can actually multiply the inverse square root of Sn to the left of this thing, which is the left-hand side of our central limit theorem. Then this will converge in law. On the right-hand side, you see I'm replacing the sample version by the population version. I'm replacing this Sn by sigma. And y was what we have in the central limit theorem. So essentially, you can standardize your right-hand side to be identity covariance matrix. So we're just saying that using the Slutsky theorem, we can get the right-hand side to be identity covariance matrix. So where the variables are not dependent. But what we're doing here is that we're doing a transformation on the left-hand side. So this is like a rotation, basically. We're rotating things and standardizing their variances. So each dimension becomes standard normal, basically. Okay. This is an example of a more general theorem due to Kramer that states that smooth functions of the sample moments are asymptotic and normal. First, it is clear from the central limit theorem that the center sample moments, such as the average of the cubics, and the average of xi squared yi are jointly asymptotic normal if the expectation of the squares of all terms exists. This is like about a finite sample condition, finite variance condition. Then repeated application of the following theorem shows that moments centered at a sample mean and smooth differentiable functions of them are also asymptotically normal. Okay, so what we're saying. So essentially, this is a generalization of central limit theorem by saying that, okay, we know for central limit theorem is this. Root n xn minus mu convergent law to normal distribution. This is what we have. Now, if you have continuous mapping theorem, right, what you will do is this. So basically, if you just use the continuous mapping theorem, but not the Kramer's theorem or delta method, you would do is that you apply the g function to the left-hand side convergent law to the G function applied to the normal random variable on the right-hand side. That's what you will get from the continuous mapping theorem. But this is not our Kramer's theorem, okay? Because on the right-hand side, maybe you have a random vector, but if you apply the G function, the result may no longer be normal, right? You can have the normal distribution transformed. But the Kramer result on the right-hand side, you still have normal, right? So you keep the normal distribution, but you are getting what? You're actually applying G to your Xn, G to your mu, and G enters the covariance term in the normal distribution. That's it. So that's why the Kramer theorem is very useful, because people prefer to have a limiting distribution as normal, because normal is such a nice distribution we can easily work with. Like you can know the 0.05, like for 0.05 confidence interval, you have the 1.96, right? Critical values, one dimension. So these are the things people like. So that's why for Kramer theorem, essentially, it is saying that, yeah, the continuous mapping theorem, this one is exact, but we're not getting there. Where we don't want this. Essentially, what we're doing is that we want to say if the G function is a smooth enough function, then after the transformation, I still get normal distribution. And basically, the effect of G only enters the covariance term based on its derivative, first order derivative or gradient. Okay, so this is the major result. That is, if you have, this is the general result, root n times xn minus mu converge in law to x, then you apply G to xn, apply G to mu, then you just you multiply G dot mu to x. And this is something as a result of Taylor expansion, basically. Because for Taylor expansion, essentially, you can approximate a function G by a linear function times the slope. And the slope is actually, sorry, I should say, you approximate the function G locally by a linear function, and the linear function has a slope as G dot, right? Or G prime, which is the derivative. That is the calculus result, and that's what we apply here. Let's look at the proof. So this is the proof we can quickly go through together because it's not very long. So we look at the general form. Root n, xn minus mu converge to law in law to x implies that xn converge in law to mu. Why is that? Why is that? The reason is because you can divide root n to both ends. And if you divide to both ends, then the right-hand side x over root n will converge down to 0. Will go to 0 in probability. Yeah. And of course in law. That's the reason. Okay, now for Kramer the theorem, we need actually continuity, not just in G, but also G dot, which is the gradient of G. So in other notes here, we use this G dot on top to mean the gradient. So it's a row vector, which is something we introduced earlier. Yeah, let me scroll this up a little bit so we can show a better full picture. Okay, so G dot is continuous in the neighborhood of mu. So mu is your parameter value. So then this continuity in the neighborhood of that is just for the purpose of Taylor expansion or mean value theorem. If you recall, we talked about this mean value theorem. We said that we can express Gx as G mu times this thing, okay? And this thing is what? This thing is that x minus mu, the difference between the two inputs. And here the slope is basically an integral of G prime or G dot, I kept saying G prime, G dot through the interval, right? We do the integration over the interval. Interval goes from mu to x. Yeah. Okay. And also in this neighborhood, because of this Taylor expansion, now you see if I apply, I move this G mu to the left-hand side, I multiply root n, and this is what I get. So essentially you see, except this slope part, this part is just what I have in my original central limit theorem, right? Root n times xn minus mu. All right, so what do we do with this? What do we do with this? So for this part, as I said, it's actually an integration in the segment from, v being 0, that is mu. V being 1, that's xn. You go from mu to xn, you do the integration of this gradient function. That's what you're doing. But we know that xn goes to mu, right? And this is what we get first. Xn goes to mu is implied by the central limit theorem. And actually, we know that for law of large numbers as well. So you have to go down to 0. So essentially, this segment is shrinking towards mu. So that's why this integral itself is convergent to this just g dot at mu. Okay, because the segment is convergent. The segment is shrinking from xn to mu. So that's why we get here. And the last part of this is application of Slutsky. Okay, so we are actually having this part converge to g dot mu, and this part convergent law to normal distribution. So that's why this part converge. And we're applying Slutsky here. Okay, so essentially, you see, this is what we get. And if x is normal, then multiplying a normal random variable by a constant vector, it means that the constant vector will enter in the square form into the covariance. And that's what we have here. Okay, so that's why we have this limiting distribution. So yeah, delta method is very widely used. We use it a lot in our derivations of the asymptotic distributions of sample moments. Okay, so let's look at one example. Example 1. For a sample from a one-dimensional distribution with mean and variance sigma squared. Okay, we have this sample mean central limit theorem result. What is the asymptotic distribution of this xn squared? Okay, so essentially, what is the g function? So to apply the Kramer theorem or delta method, you first identify the g function you need. And here the g function is the square function. Gx is x squared. Then its derivative is simple, 2x, right? And then you just apply the derivative to mu, and you get 2 mu. The reason is because if you remember in the result, let me turn the page. In the result, you have g dot mu here. So you need to apply the derivative to mu. And that's what you're doing here. Yeah, so then it's simple, right? So here it's one-dimensional. So you just have g dot mu squared. And that's 4 mu squared multiplied by the variance of the central limit theorem result, sigma squared. And that's what you get. Yeah, that's it. This example and those that follow bring out several points to be aware of in large sample theory. First, the rate of convergence to normality in this delta method can vary widely with variation in either g or mu. Yeah, because we're just using the first order Taylor expansion, remember that. And the first order Taylor expansion may not be very good, especially if you have very large g dot. That means you have a large change in your, or I should say, in other words, if you have very large g double prime, the second derivative, so which means that you have sharp change in the function's gradient, right? Then you have only the gradient as a local thing, may not be very good accurate as approximation. Okay, second, the asymptotic variance can be 0 here in this problem. You see, you have a 0 variance issue when mu is 0. Right? And you cannot allow the limiting distribution to have 0 variance because that means it's a point mass. It's a point mass at 0. You don't get a distribution. And this is called the degenerate case where you don't have a valid limiting distribution, but a point mass. That means what? That means if mu is 0, this part is a point mass at 0, it means that you don't stabilize your left-hand side enough. Because we multiply this root n to stabilize it, right? So because we know that the difference is always going down to 0 in probability, no matter what. But want to stabilize the difference into a distribution. So we multiply by root n. But if we still have the right-hand side 0, that means that the stabilization is not enough. We need to multiply something bigger than root n. That's the intuition. Okay, yeah. And this is, so you see, this going to 0. And this is not what one means by asymptotic distribution. We would like to find an asymptotic scaling sequence AN such that this has a non-degenerate distribution. In fact, we can show that when mu is 0, because you see, when mu is 0, then this difference, we can get rid of the minus mu square. We just have the xn square, right? In fact, we can show that when we change the root n to n, we have a stable distribution. It's actually chi-square distribution, chi-square 1 multiplied by sigma squared for scaling. This is just because of Slutsky theorem. You know, when mu is 0, right? When mu is 0, let me write it here, we actually have root n times xn bar convert in law to, this is the central limit theorem. And now you apply Slutsky to square both ends. And for the left-hand side, you have n times xn bar square. For right-hand side, it's the square of this. The square of a normal mean random variable is actually a scaled chi-square distribution. Because we know, like, if we just square normal 0, 1, right? If we do the square of that, it's chi-square 1. And now we have the normal with variance sigma square instead of 1. That's why sigma square times chi-square 1 as the limiting distribution. Yeah, so you see, in this case, the delta method gave you a degenerate distribution, but using Slutsky theorem, you can get a distribution. Yeah. So that's why when you derive asymptotic distributions, many times you need to be more creative, right? You need to think about which theorem can give you a stable distribution. And now here we are not talking about different, how to say, accuracy for approximation, because there is a field for your information called higher order asymptotics, which means that when they do the delta method, you are not staying at first order Taylor expansion, you can go to the second order. Yeah. And then that will, if once you go to the second order in Taylor expansion, you will have a square difference, right? Because you have x minus mu in the first order, second order, you will have x minus mu squared. So of course, if you go to that order, your asymptotics will always involve some chi-square distribution, not just normal distribution, just for your information. Okay, second example. Okay, I haven't finished the sentence. Third, the moment of the limit need not be the limit of the moment, as the following example indicates. What does it mean? The moment of the limit may not be the limit of the moment. So here, we again start with the central limit theorem. What is the asymptotic distribution of 1 over xn bar? The inverse of xn bar. So in this case, the g function is 1 over x. Then g dot x, the derivative, is minus 1 over x squared. Applying this g dot to mu, we get minus 1 over mu squared. Therefore, by delta method, when mu is not 0, because when mu is 0, you have this dividing 0 issue. But when mu is not 0, we have this result. You just square this g dot mu, that become 1 over mu fourth times sigma squared. This is what we get. However, one thing that's interesting is that if you just look at this xn, all right, if you have the xn follows normal distribution with mean mu sigma square n, so this is actually what we get as the asymptotic distribution for xn bar, right? 1 over xn bar doesn't have a finite expectation. If you just have that, yeah, this doesn't actually exist, and this is actually infinity. So what it says is interesting is that, okay, I'm just saying this. So X and bar following this is the limiting distribution, but the limiting distribution's inverse doesn't have expectation. But if we are getting the inverse to get its limiting distribution, then we can have expectation 0. Yeah, so this is also what telling you that what you can do and what you cannot do with the delta method. So what I'm saying here is that the limiting distribution, you can interpret this as it's not the accurate distribution, and yeah, it's asymptotic distribution. So essentially, this is an asymptotic mean, right? Or asymptotically, it's centered around this, I should say, centered around 1 over v. But if you just take the distribution of x and bar, the limiting distribution, and this one doesn't actually have a inverse expectation. I don't know if that makes sense to you. But this is mostly related to what we mean by expectation. But I would be very curious to see how much you can get out of computation. You can try this. So what I'm suggesting here is that you can try to use whatever distribution. It could be Poisson or binomial, and you generate large enough sample, you get a sample average, right? And you do that for many, many times, and you can plot the distribution of the sample average. And of course, it will follow central limit theorem. Now you do the opposite. How about you actually take 1 over the sample mean, and you do that for every sample, and then you plot the distribution of the sample mean. But just make sure that when you generate your sample, mu is not equal to 0. And then you can see whether this result still holds. And this is to check this result. But on the other hand, for the sample mean itself, if you take the inverse of many of them, and the expectation of the inverse, it may not expect. Yeah. So I think this is actually a very interesting counterintuitive result, but hopefully you can verify it numerically and see what you get. Okay, you can plot the distribution, but when you plot the average will be very large. Yeah. Okay, example 3. Assuming finite fourth moments, what is the asymptotic distribution of the sample variance, not sample mean? So we call that Sx squared, 1 over m, sum xi minus xm bar square. Okay. And here we decompose this into 2 terms. So first, the average of xi squared minus the square of xm bar, right? Still average of the second moment minus the square of the first moment. We must first find the asymptotic joint distribution of the first 2 moments, this one and this one. And for each one, we can apply central limit theorem. Since this Sx squared doesn't depend on location because we can shift our sample, it doesn't change the variance. We can just assume the sample has mean 0, mu equals 0. Okay, so this is what we denote. For your information, we'll use this notation for a while. This is the notation for the second sample moment. This is the notation for the first sample moment. So in other words, mxx is the average of xi squared. Mx is the average of xi. From the central limit theorem, this is what we can get, right? So essentially both are averages. We just get their joint distribution, and this sigma square is 2 by 2. And it will involve the covariance of xi and xi squared. We will have that. Okay, now Sx squared. So this is a perfect example to apply delta method because Sx squared is just the second moment. It's just the second moment minus the square of the first moment. Okay, so this is our g function. And the g function takes a 2-dimensional input and a 1-dimensional output, right? Sx squared. So we can easily get this gradient, and applying this gradient to the mean of mx is 0. We set it to 0 by shifting, and the mean of the second moment sigma squared. Applying to that, this is what we get. So then you just apply delta method. This is the vector form delta method. Sx squared minus delta square. We'll just apply this gradient on the left and right? So this is 1 by 2 and this is 2 by 1. We do that and this is what we get. So then we get this asymptotic normal distribution of sample variance. And mu4 here is another notation. It is mu4 is the fourth population moment, just like sigma square is the second population moment. So we have mu4, but actually for normal distribution, so let me just say it. Mu4, right, is this one. X minus mu, this is it. This is mu4. And for normal distribution, we can show that it's equal to this when mu is 0, because we're shifting mu is 0. So therefore, we get a very nice asymptotic distribution for the sample variance. So this is like 3 sigma fourth minus sigma fourth. So we are left with 2 times sigma fourth. Okay, that's it. So delta method, very useful because now you see using delta method, we can just build on central limit theorem and we can now apply it to derive the asymptotic distribution of sample variance. Okay, now improving the approximations. As seen in example 1, there is a danger of using the Cramer's theorem when mu, this should be in the notation to be corrected, mu is close to 0, right? You can have either dividing 0 issue or degenerate limiting distribution. One can often obtain a definite improvement in the approximation by taking more terms in expansion of the Taylor expansion function of G into account in the proof. Okay, let's take a look. Let's go to the second order. Suppose that we still have the central limit theorem as a starting point, and suppose we are interested in estimating G mu, where G mu has a continuous second derivative that is not 0. To improve upon the approximation given in the Cramer's theorem, we expand gx to about mu to second order terms and complete the square. Okay, so now we're actually not going, we are not staying in the first term, we go to the second term. So we need the second derivative. And then you see that what we're doing here is nothing special. So we move G mu in the Taylor expansion to the left-hand side. First term, second term. We're just combining the first term here into the second term. So we get this combined square term. And we create this x minus something squared in one term. Okay, now replace x by xn. This is what we get. And essentially, you see what? You see that the root n xn minus mu, this is what we get from the central limit theorem. It's now in the second term, but we are scaling it. We just shifting it. We are also shifted and then we square it. So essentially, if you just have this term by itself, then you square it, that's chi-square. But now you have the scaling and shifting. So it's not so simple. But we're going to say this is general form of doing the second order expansion. And the distribution of the square of a normal random variable with mean gamma and variance 1 is the non-central chi-square distribution with 1 degree of freedom and non-centrality parameter gamma squared. So therefore, we can rewrite this whole thing because basically this term, just for your information, this one has asymptotic distribution, limiting distribution to normal 0, 1, right? That's fine. And it's normal 0, 1, first shift by gamma n and then square. And we refer to this as the non-central chi-square 1 distribution. That's it. And then we shift distribution again by gamma n square. And then we multiply by what's outside here. Okay, so essentially, this can give us a different form of asymptotic distribution. And because this is a second order delta method.
non-central question? Is it like just shift?
So okay, you can read the sentence again. The distribution of a square of a normal random variable with mean gamma and variance 1 is the non-central chi-square distribution with 1 degree of freedom and non-centrality parameter chi-square. So essentially, this is saying this. Let me just write it. If we have z follows normal gamma 1, okay, not mean 0, then z square follows this non-central chi-square 1 gamma square. That's what it means. Yeah, yeah. Okay, yeah. And this when gx squared is when gx is x squared, this gives the comparison to equation which we just showed, right? So we have this n minus this and this. When mu is 0, this reduces to that result we get from the Slutsky theorem. Remember that. So essentially, in this case, if you have the degenerate case of using delta method, there are two ways to do. One is to go consider Slutsky theorem or continuous mapping theorem. The other is to go to the second order in your delta method. Yeah. So how much improvement, or so this can also give you an idea that asymptotic distribution is not unique. You can have various ways of getting asymptotic distribution, depending on which one is better approximation. And that actually depends on your mu, depends on your true parameter value. And that's a little bit awkward because in many cases, we don't know the true value. That's why we're doing the inference, right? But if you're doing hypothesis testing, it's a different story. Because in that case, in your null hypothesis, under a null hypothesis, you do have the true parameter value set, usually 0. Yeah. Okay, now let's look at a final application of what we said. Sample coefficient, correlation coefficient. We showed at the end of last lecture that the t statistic, remember, is the sample mean minus mu divided by Sn, right? Sample standard deviation, that's the t square. And this one, if we standardize it, and actually, you know what, the root n minus 1 is actually coming from this unbiased estimate thing. Yeah, coming from that. So this converged to standard normal distribution. So, this is also a very important result for, undergraduate level mathematical statistics. That is the t distribution. If we let the degrees of freedom to go to infinity, it converges to standard normal distribution. But the t distribution is more heavy-tailed, right? When n is smaller, Tn is more heavy-tailed. Is asymptotically robust or asymptotically distribution-free within the class of distributions of finite second moments. In particular, the confidence interval for the mean mu of a distribution given by, you must be familiar with this. To infer the mu, we can actually use the t distribution, right, to get us the confidence interval. Has approximately probability 1 minus 2 alpha. Alpha is the critical significance level, whatever be the true distribution of xi, provided it has finite variance and n sufficient large. What does this say? This means that even though your sample may not be from a normal distribution, but as long as your sample size is large and your sample has finite second moments, you can still apply t-test. You can still do the t-test. That's a very important result. And that's why t-test is so popular, because as long as your n is large, it's working. The usual test or confidence interval for the variance of distribution. Okay, now variance. When sampling from a normal distribution is based on this statistic, you are using the sample variance Sx squared as your basis for the test statistic, and you do the scaling. You can make it follow a chi-square distribution with n minus 1 degrees of freedom. So this is also from the old days, because in the old days, remember, it's very difficult to calculate what's the tail probability without computer. So people spend time making those tables, right? The t table, the chi-square table, but you cannot rely on additional parameters. So that's why t n minus 1, chi-square n minus 1 are parameter free. They're just their own thing, right? Once you know the degrees of freedom, you know the sample size. In other words, you know the distribution. That will make the table lookup possible. But again, I would say these are the old strategies before we have computers. Example 3 shows that this test is not asymptotically distribution-free because the asymptotic distribution of this depends on the fourth moment of the true distribution. Yeah. So basically, if you have asymptotic distribution depending on other parameters, there's a problem. We can also use the Kramer theorem to find asymptotic distribution of the sample correlation coefficient. So this is what you have learned before. Remember, essentially, notation-wise, let me just quickly remind you. This is basically sample covariance of x and y divided by the square root of the sample variance of x times the sample variance of y. That's it. Yeah, this is the sample Pearson correlation. We use it to test the hypothesis about the population correlation coefficient, the population covariance over the square root of population variance times population variance. Okay, this is the major result. If we have paired samples, x1, y1 paired, x2, y2 paired, a sample from a bivariate distribution with finite fourth moments, expectation of x4, x to the power 4, expectation of y to the power 4. And this is the first step before we get a correlation. So first, we derive the joint distribution of the sample variance of x, sample covariance between x and y, and sample variance of y. Okay, the three things jointly follow a normal distribution, and their mean is the population version. The population variance of x, population covariance of x and y, and population variance of y. And on the right-hand side, these notations, they are just used for simplicity, notation-wise simplicity, but they're basically calculating the all sorts of covariances. Yeah, that's basically it. Okay, if you can get this joint distribution, then you can get the distribution, asymptotic distribution of sample Pearson correlation. Essentially, because R is just a function of Sx squared, Sxy, and Sy squared, right? It's Sxy divided by Sx and Sy. That's why we can just use the delta method. Okay, and if you apply the same function, we can call that a g function. The g function takes as input Sx squared, Sxy, and Sy squared. Three-dimensional input, and the output is one-dimensional R. We apply the same function to g function to the mean, sigma x squared, sigma xy, and sigma y squared, and you get the one-dimensional output as the rho, which is the population Pearson correlation. And then you just apply that g prime, right, g dot, rho vector gradient, right, multiplies this matrix, and then right multiplies the transpose of that g dot. You get this gamma square. And the gamma square has this long form. Yeah. So it's basically algebra. Yeah. You need to have those moments to get it. Okay. But as you know that essentially you need to know the population moments to actually calculate the gamma square. But in practice, how do we do it? Or for example, for central limit theorem, to apply it, we have sigma square, population variance on the right-hand side, on the limit in the limiting distribution. How do we calculate that? We don't know it. So therefore, a strategy commonly used is called plug-in. That is, you just use an estimator instead of the true variance in the limiting distribution. All right, I know this looks a little complicated, but once we have the sample x1, y1 to x and ym come from a bivariate normal distribution. If we have that, it's not complicated. Let's look at this. So we will calculate all these complicated moments above under bivariate normal. Okay, so this is the gamma square. We need to calculate this. How do we do that? To find the values of gamma square for the bivariate normal distribution, we may assume the means are 0 and the variances are 1, because gamma square, which is the moment, is independent of location scale. The reason is if we go back to here, we can see that if you look at here, these things have already subtracted the the location. Locations are gone. And also when you do those division, the scales are gone. So that's why gamma square is independent of the change in location scale. The moments, this one, x cubed y, may be found by integrating or by taking appropriate derivatives of the characteristic functions. You know, another way to use the characteristic function is to get moments, to easily get moments by taking derivatives. Anyway, so under the normal distribution, a lot of things can be simplified because in the normal distribution, bivariate normal distribution has only how many parameters? Bivariate normal. Bivariate normal means two-dimensional normal distribution. That's bivariate normal. It only has 5 parameters. The mean of x, mean of y, variance of x, variance of y, and correlation. Yeah, that's it. Yeah. So here we can simply find all these higher moments, right? They can all be expressed by the 5 parameters I just said. Then gamma square, very nice, can be reduced to just 1 minus rho square. So rho is the true Pearson correlation between x and y. So it's 1 minus the Pearson correlation square, difference squared. Okay, hence for bivariate normal, this is all we get. So this is the asymptotic distribution of the sample Pearson correlation around true Pearson correlation. And the variance, of course, you scale it by root n to make it stable. Not degenerate. The variance is just the square of 1 minus rho square. That's it. Okay. Any questions? I would say this is like the culminate application of this delta method, right? So we just show how you can use it. Of course, I skipped the kind of tedious algebra steps, derivations, but these are the things you should be able to fill in. And sorry?
Oh.
Yeah, especially, you know, for this kind of algebra, at least in previous years, you can do it using their software called Mathematica, right? So it can help you do this algebra. Yeah. But anyway, so basically this is a very nice clean result when the sample comes from bivariate normal. But if the sample doesn't come from bivariate normal, you need to estimate those higher moments from your data. Yeah. Okay. And in application, like I said already, how would you do it? Rho is unknown. Let me just give you one example where we have the hypothesis testing. What if the null hypothesis is rho is 0? This is common, right? Because we want to answer the question, that is, are my x and y correlated? Based on my sample, how can I decide that? In this case, you will have a nice result, that is the root n times r, your sample correlation, which will for sure be not exactly 0, right? But we just want to know whether the magnitude of r means we can rule out the possibility that rho is 0. And we know this will converge in law. Since rho is 0, we just use 0. Standard normal. We can use that. Yeah. So this is a very simple result for you to decide, compared to standard normal, is my r large enough, right? Okay, but if your rho is unknown, for example, if you want to provide a confidence interval, right, then you need to plug in rho for using R. Use R to plug in rho, and then you can get that confidence interval. Okay. Another thing I want to say about is the so-called robustizing. The usual chi-square test for variance based on the fact that for normal distribution, so if your sample comes from normal distribution, then your sample variance scaled by n over sigma square has a chi-square distribution with n minus 1 degrees of freedom. And one fact, I don't know if you know that, is that when your n is large, the chi-square will become more like a normal distribution also. You know, chi-square, when n is small, is very asymmetrical because chi-square only starts with from 0, right? Doesn't have a negative domain. But you'll actually see that. Let me just quickly draw it. So chi-square is a positive, it has positive values. So basically this is 0. So when n is small, your chi-square may be something like this. So very right skewed. But when n is large, so something you should know is that for chi-square, let me put it n here. Okay, its mean, or here, I don't know. Here, the mean might be here. The mean is always n, so its mean is n. And the variance is 2n. So you know those two things, right? But when n is large, the distribution will be more like n is a 0 is still somewhere far away now. The distribution will be more like symmetrical and with the center at 0. And even though, normal distribution has this domain real line, right? It should have negative values, but normal distribution is also very heavy, very light tail. So you can neglect the fact that there's a small chance of getting negative values because it will not happen most likely. So that's why it's an approximation. Yeah. This also gives you an idea that asymptotic distribution may not be theoretically rigorous because you can see chi-square shouldn't give you negative values, but this one potentially give you a negative value. But it's so small probability that we don't care. That's it. Yeah. Okay. So it can be approximated by this normal distribution. Hence, the confidence interval for sigma square obtained from the test can be, you can just standardize this to get a standard normal distribution. Okay, and then you can use this to get a confidence interval. Yeah, you're using the asymptotics of chi-square. Yeah. But if the population is not normal, we can use the result from example 3, which is what? Which is what we get from here. Let me try to go back here. I can use the example from this one. We can get here. This is what we previously get. So this is the asymptotic distribution of Sx squared, right? Around its true population variance. We can use this result instead of the exact chi-square distribution result, because this one required that the sample is normal. So that's why this one has chi-square. But this is exact result. If your sample is not normal, you can use central limit theorem or delta method result. Following what I just showed you, you will get this one. But again, there's a problem. The fourth moment is not known. The statistic cannot be used directly. However, it can be robustized by replacing the coefficient of kurtosis, the fourth moment, by an estimate. So this is what I call the plug-in. So essentially, you are not using what if your statistic, right, on the left-hand side involves any true parameters, you have to replace it by plugging in the estimates. So I think this can also say something about statistics. That is, even though I would say there are two kind of opposite forces in doing statistics. One is that we try to be rigorous. We try to tell something about the population from our sample. But on the other hand, in many cases, we have to be approximate. For example, if the statistic involves unknown parameters, we have to do plug-in, then that is approximation. So therefore, because of this kind of, how to say, subjective choice, and that's why I think it's not mathematics, because mathematics is accurate, right? You have absolutely right or wrong, but this is not. A lot of the cases it's your choice, how much relaxation you want to go to, right? How much approximation you want to use. That makes it kind of like art. That's why many people say statistics is like an art. It's like a philosophy and art and mathematics. I would say nowadays maybe more of computation as well. So that makes it kind of hard, I would say. I would say something more general than specific practices to me is the general idea. Like, how do we think about inference, right? What do we want to do? That is more important. Because if you come down to a specific problem, people may tackle it in different ways. Do you want to say something? Yeah, I think you have a lot of facial expressions.
Sorry.
How about how about you guys? Yeah. Yeah. Yeah.
Like regarding this topic.
Yeah, anything. Yeah. Because I feel like especially if you use statistics in your research, there are a lot of subjective decisions you have to make, right? Yeah.
Of course.
Yeah.
Like, the reason I bring this bachelor's degree in statistics is because when I'm running experiments,
Mm.
I kind of like show some a little bit different, like in stories based on like a model specification.
Yeah,
So,
yeah, exactly. If you,
Yeah.
because the same data, you use different models, you get different conclusions, right? Then the question is, how do you choose your model? Yeah. One thing I really want to say, which I really like, is this result. I think it's very elegant because earlier, right, just a few minutes ago, I said that if you don't know the role, because it's in your limiting distribution, you have to do plugin. But there is a smart way to avoid that. It's called variance stabilizing transformation. I think it's a very smart idea. The idea is to transform everything on the left-hand side to make the right-hand side the distribution parameter free. That's what we hope to achieve. So we seek a transformation GR, and then we hope to use the delta method. So basically, after transforming the R and rho by G, the right-hand side becomes parameter free. Okay, how do we do that? So this is the covariance stabilizing. So essentially, we know based on delta method, we will multiply G dot, right, which is the derivative at rho square to the variance. If we want to set this to 1, then we can solve what is the derivative to find the G. That's the idea. So we know this is 1, and this will give me G dot rho, the derivative is 1 over 1 minus rho square. And then given the derivative, we use integration to get the G. And that's what we have. And with that, we just apply this to everything. So essentially, the statistic is no longer R, but this log of 1 plus R over 1 minus R. And this will follow standard normal distribution, which is very interesting, right? So essentially, you're doing transformation on your statistic, and then you are getting rid of the parameter on your right-hand side. Yeah, this is called variance stabilizing transformation. Okay, any questions?
Can we go about to Taylor? Or should we even go about to?
So I said there is a field, I think it's a small field in statistics called higher order asymptotics. They usually go to 2, but I do see some people went up to 3. Yeah, yeah. But the question I think is ultimately how accurate is Taylor expansion is, right? Yeah. It's not always that you go the higher order, the better, because that also involves assumptions. It's not, yeah. So anyway, but you can check it out if you are interested. Yeah. Okay. Any questions? If there are no more questions, I think we can move on to our next topic. Yeah. Basically, we finished today. We covered a lot. We finished the central limit theorem variance, right? Limburg-Feller, M-dependent stationary sequence. And we talk about delta method. We applied it to sample moments, right? For example, sample variance. And we then apply it to sample correlation coefficient. And then we talk about the variance stabilizing transformation. Okay, so these are the very practical things people use in deriving limiting distribution of statistics. But in the old days, maybe we don't know the limiting distribution for many statistics, so it's worth doing so. But nowadays, the field has been here for so long. So maybe for some common statistics, you already have the limiting distribution. So you don't need to derive everything from scratch. Yeah, but later we'll show you some more general results for maximum likelihood estimator. Because in many cases, you will propose a model for your data, and then you can derive the MLE, right? Maximum likelihood estimator. And then you can derive the asymptotic distribution of the MLE. So that is like a more general strategy.
8349.
Oh,
That's next door.
This is 259.
Okay. Yeah. All right. So I want to say that for MLE, right? So if you can have the asymptotic distribution for MLE, so for many practical problems, you can just use that because it's a more general form. Okay. Okay, if there are no more questions for the remaining time today, I will move on to our next topic, which I think is a fun topic. It's called order statistics and quantiles. This is also very useful because in many cases, we may be interested in the quantile of a distribution, not just the mean. Because, for central limit theorem, everything we covered so far, it's more concerning the mean and the variance, which are all like mean parameters. But quantile is different. So for example, if you want to know what's the center of the distribution, we can talk about the mean and we can talk about we can talk about the median. What's the difference? What is the benefit of using mean or variance? Have you ever thought about that? Oh, sorry, mean or median. Sorry. What is the benefit of using mean or median? What's the advantage of using either one?
If you use mean, you can get skewed by extreme value. If you use median, it's hopefully more balanced out.
Mm-hmm. What do you mean by balanced out?
If you're taking middle instead of taking the sum and then dividing over everything.
Okay, what's the benefit of doing that then? What does it imply in practice? Because, when we use a statistic, we always want to inform people something, right, from our data.
Well, it's kind of very useful to use them together, like
Mhm.
compare it between,
Two things.
like to use the median, you already know where the 50% of the data.
Yeah.
So
Yeah.
it gives you a lot of information
Sure.
when you compare it to the
Yeah,
mean.
exactly. For example, income, right? When people look at the mean and the median, they can be very different. The mean is usually, well, mostly higher than the income because you have people who are extremely
Mhm.
rich, but they are very small proportion. But if you calculate the mean, then they will drive the mean up, but the median won't be affected by them, right? Yeah. So that's why median is also used as what people call the robust statistic. It means it's not affected by outliers. But if the outliers are informative, then you need to reflect them in some way, and median won't do that. So that's why it's very important to think about what the question is. Okay, so order. Consider an ordering of n real numbers. A vector value function n, fn, that maps this to be a permutation. Essentially, this is what I mean. So we have a sample, x1 to xn. We sort them from the smallest to the largest, and we call the smallest x1 in parentheses, x parentheses 1, and the maximum x parentheses n. And x parentheses I is the ith order statistic of the sample. But please note that the notation xi does not explicitly use the sample size n, because you only say it's the ith one, but you lose the sample size information. But sample size here is critical, because if you change your sample size, then the order of this may be changed, right? It may no longer be the same random variable, may not be the ith one anymore. So it depends on it. So that's why for some textbook, they use the more complicated notation to record the sample size. So 1, comma, n, yeah. But here we use the simpler notation, yeah, just for information. So extreme order statistic, what does that mean? It means that you are concerning the maximum or the minimum. The asymptotic distribution of order statistics as the extreme of a sample may be derived without any specialized knowledge other than this very important formula, which we introduced in the first class. That is 1 plus c over n, the sum raised to the power n. And this will converge to exponential c. Yeah, so n is gone. So this is the thing we will use again and again. And it's generalization. The generalization can be that we let c become cn, but cn converges to c. We let n become bn. We let bn diverge as n goes large. So we can be more general, but it still converge to the same limit. Okay, recall that by asymptotic distribution of x1, we mean sequences an and bn along with a non-degenerate random variable x. By non-degenerate, we mean that the random variable does have a distribution. It's not a point mass. We can do this, how to say, minimum, the smallest order statistic, subtract by bn. Bn is something it will concentrate on. Multiply by an. An is usually a divergence sequence to stabilize it, like our root n, for example. And then together, this will converge in law to this non-degenerate random variable x in distribution. That's what we want to have. And for doing so, we can actually get limiting distribution. We call this the limiting distribution of our minimum statistic. And why do you want to do that? So for example, the most immediate application of knowing the distribution of extreme order statistic is that you can use it to estimate the boundary of your data generating distribution. And what is a true minimum? What is true maximum? Because my sample minimum should always be larger than the true minimum, right? Because I can never reach that. And my sample maximum is always smaller than the true maximum, but we just want to know how far away they are. Yeah, so that's the application scenario. So example 1, let's look at some examples to help you get started. Suppose x1 to xn are independent and identically, we usually talk about uniform 0 to 1 random variables. The reason of doing that is also very, twofold. One is that we can get some very nice theoretical result from this. Second, for any sample, you can actually transform them to become uniform 0 to 1 by using their empirical CDF function, right? Because you can just use the CDF function to rank them, and then you get the quantiles, you get the percentile, actually the probability that is the smallest, second smallest. You can order them to become uniform 0 to 1. That's achievable in practice. And that doesn't change what's the maximum, what's the minimum, because it preserves the order. Okay, if you have such a sample, uniform 0 to 1, what is the asymptotic distribution of xm, the maximum? You know that the maximum should be close to 1, but not exactly 1. And how close it is to 1 depends on its sample size, right? You can imagine that if n is infinitely large, then the maximum will be very close to 1. That's what you can imagine. But let's just know the distribution, right? To what degree? That is the question. To what degree? Okay. So we will use this very interesting probability exercise. I think you have tried this before in some undergrad class. So if the maximum is under t, it will imply that every random variable in the sample is under t, right? They are equivalent. So therefore, you can calculate the probability that x maximum is under t. And this is the definition of the CDF function, right? CDF function is always the probability that a random variable is under some t. So when t is less or equal than 0, that is impossible, right? Your sample has domain 0 to 1. Then this probability is 0. When t is between 0 and 1, that means every xi is under t, and that is probability t for each xi to be under t, since it's uniform 0 to 1, and they are independent. So it's t times t times t for n times, that's t to the power n. If t is greater or equal than 1, then for sure the maximum cannot be larger than that t. So it's under this t with probability 1. So this is what we get for the distribution for xn maximum. It's obvious that this xn converges in probability to 1. Why is that? Because, first probability is 0. Second probability go down to 0 as n goes to infinity, because t is between 0 and 1. Then the probability, then xn will be what? So be a point mass at 1, right? Yeah, then it's converging probability. Yeah, what I'm saying is just exactly what's in this formal proof here. But this limit statement does not fully reveal the asymptotic distribution. It's just telling us it's consistent. It's consistent it's a consistent estimator for the upper boundary. We derive sequences an and bn in this form, like we said on last page. So this has a non-degenerative limiting distribution. Evidently, we should expect bn to be 1 because that's the limit, right? That's where the xn is convergent to. So how can we find an? Like how much inflation we do need to multiply to stabilize the distribution. Okay, so to do that, we just assume that we want to derive an and bn. And we hope that this statistic has a nice CDF function. And this is the CDF function. F at t is the probability that the statistic is under t. And then we just keep xn maximum on the left-hand side. So xn is under this thing. Okay, so first of all, we want this right-hand side to be in this range, to be between 0 and 1, since the maximum is between 0 and 1, right? So as long as an is positive, we actually found this ft to be this between 0 and 1. And we want this to be some CDF function of a good limiting distribution. How do we do that? So again, we want to keep the form this because we know Bn is 1. We want to set Bn is 1 is the limit, and we want to have this An diverging, right? So why don't we just set An to be n? So then this is the limiting, this is the CDF function, and its limit is exponential t. We're using the fact we showed before. However, we're not finished yet since we have not determined which values of t makes the limit valid. There is a requirement in equation, this one, that this is between 0 and 1, which in this case becomes t over n is in this. This means that t may be any negative real number, since for any t less than 0, this is for sure less than 0. So we satisfy this requirement. So in other words, we derive this range for t. That is, if t is less or equal than 0, the limiting CDF is exponential t. Otherwise, it's when t is positive, is 1. So in other words, we can actually show that this is the what? This is actually the, if we take t to be negative, then this is actually the exponential function distribution. So exponential random variable has a positive value, but its negativity minus t takes negative value. So we're actually having that. So essentially, we're saying that minus n times xn minus 1 converges to t, and minus t follows exponential 1. And we get the limiting distribution. So what we could do finally is to reverse 1 and xn. So we write this way. And so this follows, this converges to exponential 1. And this makes sense because xn is always less than 1. Right? So 1 minus xn is positive, while xn minus 1 is negative, right? So in this case, we go through all those thought process to arrive here. So what is nice about this result is that we found this limiting distribution is a well-defined exponential distribution, and we find this inflation factor to be n. So essentially, we can stabilize the difference. 1 minus xn, we know it's going down to 0 in probability, right? Xn is going to 1 in probability, but we can stabilize the difference. We find the rate is n. So with multiplication to n, it stabilizes as an exponential distribution. This is a very nice result. So basically, the difference between the maximum and the upper boundary, right? That's it. Okay, so we can go to the next example, and then I think we can conclude today. Next example, the only change we make here is that we change uniform 0 to 1 as the sample generating distribution to exponential 1. Okay, so now x1 to xn are IID from exponential distribution. Again, we are interested in the asymptotic distribution of xn. So following this example 1, we would like to compute the distribution of this form as well. So the question is always to find Bn and to find An. Okay, previously Bn is 1, right, as the upper bound, and we find An as 2. Bn is 1, An is n. How about this? So we follow the same idea, try to express the probability that the maximum is under something as the product of every random variable is under the same thing, right? The power. And then we just use the CDF function of exponential 1 because we know every xi follows exponential 1. We put that in, raised to power n. But of course, we need a condition on this as well because exponential function has a domain, distribution has a domain in the positive real line, right? Positive part. So we need this to be positive because otherwise the CDF is 0. Okay, so what do we do? So now in this case, the question is, looking at this again, the question is how do we make this in the form that we are familiar with? Remember, we need a form like 1 minus something over n to the power n. We need to make up this form. And so the question is how do we change this form to be like this? And here we can take Bn to be inside here to be log n, because once log can cancel with exponential, we can take a to be 1, and that will give me this form. So essentially I'll have what? Exponential minus t over okay, so basically, let's look at this. Exponential minus t minus log n. That's what we said. So this is just e to the minus t over n, right? And that's why we create this form here. And as n goes to infinity, this will converge to exponential of minus exponential minus t. And again, here you need a condition to have this positive, and you have an1, bn minus log, bn log n. So this will translate to that. And which holds for all t as long as n is larger than this. So essentially, you can actually show that by coming back to here, by having this form, now we have decided that it's just xn minus log n. We have decided on this because an is set to 1, bn to log n. So once you have that, then you can have xn minus log n converging log to some t. And the t has this distribution with the CDF function, which is this. And actually, people define this CDF distribution to be called Gumbel distribution or extreme value distribution. So it has this common name. And it's actually used to refer to this scenario. So essentially, we know that, how to say, in this case, we don't need a stabilizing function. We don't need a stabilizing factor. We're just taking xn, subtracting log n, and show that their difference has a stable distribution, regardless of n, which is very interesting. This tells you what? This tells you that if you have an IID sample from exponential 1 distribution, the maximum is actually increasing in this order, in the order of log n. Yeah, because exponential distribution, exponential 1, has a domain that's unlimited on the right end, right? Just from 0 to positive infinity. So supposedly, the larger the sample size, the larger the maximum. There's no limit on that. But this tells you that you can get a rate. It's actually increasing in the rate of log n because their difference is actually following a stable distribution. Yeah. So this is very interesting. So even though I know it may look a little bit, how do you say, out of nowhere for you, right? How do we come up with this and this and this? But the justification here is just try to create a form of this so that we can have a limit. Yeah. I think it's a very interesting trick in this part of the lecture. Okay, I guess we can stop here today, and next time we'll come back, right? Next Monday we'll come back and I'll do some recap on the extreme order result we did. And again, I would suggest that if you're interested in doing more exploration, try to do some numerical simulation on your computer. You can see whether this really happens, right? And that's the magic of mathematics. Okay, so thank you, and I'll see you next Monday. Yeah,
Thank you.
Bye-bye. You can find it